All right, here we go. Physics reaction video number 18. Maybe some energy, maybe some springs. See how it goes.
Greetings everyone, this is Mr. Mullen, and today I'm doing a podcast going through energy homework number 3. I'm going to go through a couple examples so I can give you a work through of a couple of these problems so that you'll be more successful at this worksheet. Notice at the top of the worksheet, feel free to pause this video and take a look at all those equations relating the different types of energy we've looked at, including the types of units that you should have when you get to the end. Alright, so we're going to go ahead and get started with question number 3. And question number 3 says a 0.4 kilogram block is placed on a spring and compressed 0.20 meters. And so if I look at this picture over here, it gives me the displacement and the spring constant of that spring.
Cool.
After it's released, to what maximum height does the block reach? Okay, so we're basically looking for how much our vertical height has changed. How fast was the block moving when it was at half its max height?
So really a couple of really interesting things. I'm always struck by these spring problems, right? Because you put it on, and I'm guessing this is the spring when it's just resting there. When you rest it on there, it's compressed. After it is released, this is an interesting problem because if you put a mass on a spring, it'll just sag down, right? And eventually it'll sort of wobble, and come to a new resting place, and then you can let go and it'll just sit there. So that's not what they're saying. They're saying you've compressed it when they tell you what the spring constant is. Okay, that's what I was missing. So we know what the spring constant is, and we can figure out how much it's been compressed, and then it's going to let go. And then I'm always curious, do the students think that after it goes boing, right, does the spring keep pushing past its neutral place, keep going? I mean, it doesn't, right? The force actually is starting to pull back at that point, and a really interesting question is, at what point does the spring let go of the mass? But what's cool about this problem is I'm guessing we're going to be able to do it with just energy. Like, okay, we've stored some energy in the spring, we're going to go kablamo, we're going to assume that the spring, doesn't hold any energy and the block is sitting way up here, with some gravitational potential energy. And then I really like this second question about half its height, because all of a sudden it's like, whoa, hang on a second, I got to do a little bit more work. So let's see how it goes. Oh, the other thing I was going to say, comparing and contrasting, giving the students the drawing versus encouraging them to draw it, right? Against the scaffolding thing. So sometimes when you write the problem, it's just not clear, and you just need to give them a picture like, oh, okay, that's what you mean, right? And then there's other times when you're like, no, I think that is well described. I think that you should be able to draw that. And then if the student draws it horizontally or something, you have to deal with it, I guess. And I love this scaffold as well. Obviously, this was not part of the problem. So anyways, let's keep going.
And so we're looking for how fast velocity is equal to question mark, and this is going to be at basically 1/2 of that max height.
I love setting the question mark position.
So when I look at this here, you can include what's in your system. So I'm going to include the block. I'm going to include the spring so that I can keep all of that elastic potential energy within my system. And then I'm going to include the earth.
Ooh, okay, cool.
And so now that I've included my system, let's look at what types of energy are present. And so it's not moving. Now GPE, it's obviously from the ground. However, I can choose where y equals equal to 0. So I'm going to make my problem a little bit easier, and I'm going to make y equals 0 at the bottom of the spring. And because energy is conserved, even if this spring shoots up the block and it comes back down again, it's never going to get more elastic potential energy than it currently has. So it's never going to go below that mark. So there's our initial position. And so I'm going to say there's no GPE. Elastic potential energy, lots of that, and I haven't dissipated any yet. So I'm just going to go ahead and give this thing, say, 4 blocks of elastic potential energy.
Or 5.
To start with. Afterwards, I look at my final situation up at the top. It has come to rest.
So just that simple little thing that I did. He said, so 4 blocks of energy, at least I think that's what he said, and then he drew 5, right? So did he notice it? Did he not notice it? Does it matter? Do you have students who are just going to freak out about that, right? And so I think that It doesn't bother me at all that he's cruising along here because he's really just going to show where this energy goes. It may be that he'll just start saying 5 at some point. Um, but it's really, I would love to hear in the comments, how crucial is it to address those kinds of concerns? Do you set the culture in the classroom like, yeah, of course I meant 4, or of course I meant 5? Um, at what point do you need to address it? Because there's other students who are like, yeah, I got that. Let's go. Come on. So I just find that really, really interesting. I'm just curious to see if he catches it. And by the way, it's possible I misheard it. Let's go back and see. Go back about here. Let's listen.
This thing, say 4 blocks of elastic potential energy.
Yeah, you know what? I think he caught it right there. Did you see how there was a little bit of a pause before he drew that last little block? He said 4 blocks, and then he stopped drawing for a second, and then he kept going. So let's keep an watch out to see what comes of that.
To start with. Afterwards, I look at my final situation up at the top. It has come to rest. Now some of that energy has been transferred into the gravitational field of the Earth. The spring has sprung. I'm going to ignore drag or air resistance for this type of problem.
Cool.
Because it's going to be difficult to calculate that. But I'm going to go ahead and transfer then all my blocks into 1, 2, 3, and I gave a little bit too much.
Aha.
4. Okay. So there's our energy.
Wow.
Oh, I didn't do that.
So that was so interesting, right? So he's like, oh, wait, I wanted only 4. I may have just paused him in mid thought there. He might be going to fix the other one. Very cool. A couple other things. I'm just going to ignore this dissipation because for this problem it's going to be harder to calculate. But what I love about it is this graphical approach, this LOL approach, allows you to say, oh, okay, well, if there's just some dissipation, this has to come down. That's super, super cool. It kind of looks like there's no kinetic energy in this problem at all, but for part B there will be, so that's super, super cool. And then the elastic potential energy, again, setting this equal to 0, when he figures out how much this is, he's going to have to say, oh, wait a second, it was compressed 0.2 meters, so then he's going to have to call delta x 0.2. So he's got y's and x's in here. That's interesting. I'm curious to see if he sort of says, oh, well, I meant y or I meant x, but it's really cool.
The other one. So what I'm going to do now is I'm going to, there's our 2, 1, 2, 3, and I gave a little bit too much. 4. Okay. So there's our energy. Oh, I didn't do the other one. So there's our energy. Oh, I didn't do the other one.
Okay. So that was fascinating. He said 4 again. He drew 4. He drew 5. He's like, oops, 4. Then he's like, oh, I need the other one. So again, it's so fascinating. He could have gone back and corrected this one. But I think that from a sort of cognitive load, I'm guessing it's better that he did exactly what he did, which is to correct it right here. So that people watching this video, like right at this moment, can say, oh yeah, this makes sense. So very cool.
So what I'm going to do now is I'm going to make a equation relating the quantities of energy involved. And so simply I can do that. We have the elastic potential energy of the spring was equal to, there were no energy transferred in or out through work, and so that means that we had left our GPE. And so I'm going to rewrite now EP is equal to GPE using how I can calculate each of those. So when I look at elastic potential energy, this is just 1/2 K delta X squared.
Okay, so there
and that's equal to GPE, which is just equal to M times G times my delta Y. Now, what I like to do is I like to rearrange this equation here and then plug in numbers. Sometimes when you do that, especially when you're dealing with kinetic energy and GPE, you're going to find that variables will cancel out. Now, in this case, none of these things will cancel, but sometimes you can get rid of mass completely. So I'm going to go ahead and rearrange this and then plug in afterwards. So I'm going to get delta Y by itself, divide both sides by mg, so those cancel, divide this side by mg. And so now I have what delta Y is equal to. So my delta Y is equal to 1/2 my spring constant K, which was...
We're just going to pause right here because if I recall what's given in the problem, he actually knows delta Y. Oh, no, that's right. He knows delta X. I'm really curious about this XY mix when they're both in the vertical direction. Let's see. So solving for delta Y. Yeah, okay. This makes sense. What's curious is... Yeah, so then that delta Y is going to be measured from where that drawing was. Okay, cool.
I look at the problem over here, 320 newtons per meter. And that's all multiplied by delta x squared. The spring's displacement was 0.20, and we're going to square it. And that's all divided by mg. I look at the mass given in the problem, 0.4 kilograms, and that's times...
So you said the mass was displaced by. So for delta x, it's using displaced. That's cool.
Unit-wise, we should be left with a unit of distance. Don't forget my meters thing. Okay.
Sneak it in there.
So meters cancels meters. One of those meters cancels.
Oh yeah, this is cool.
Let me just redo this. Okay. So this meter cancels with one of those meters.
That right there. That, what he just did, let me just get it back there. What he just did, I do this all the time, right? Like you've got two of these, let's cancel the 2 and cancel the m. I think students need scaffolding for this, and my guess is, given where this tends to land in a typical curriculum, they've been seeing this kind of stuff a lot. But I think it's really, really subtle, right? Because you're canceling a 2 and then canceling an m. This doesn't have units, right? Like, what's going on? So I'm curious in the comments, like, is it better to just write another one of these so you could really cancel some stuff? Write m times m so that you can cancel some stuff. I'm really always intrigued by that. Certainly when I'm doing my work, that's exactly how I would do it. Oh, I can do it, boom. But what's curious, of course, is that this 2 needs to stay there for the 0.2, right? So you're not really getting rid of the squared. You're just doing it from a units perspective. And so this is subtle, right? So I think that he's just trying to say right now, say, you guys, the units work. And I've talked about this before. If you do everything in the common sort of SI units, the metric units, the common SI units, you can trust this is going to end up being meters, right? Because everything is built to give you meters back. And here he's just showing it, right? But be careful about crossing off that 2 because you're going to need it when you plug it into your calculator. So that's really, really interesting.
This newton down here cancels with that newton up there. This kilogram cancels with that kilogram. And so you're left with meters, and that's right. So our delta y is going to be equal to 1.6 meters. It's going to be our change of position. And so we're going to go ahead and say that we made it 1.6 meters from the starting point. I don't know how far it is off the ground, but...
Okay, so this is about a pound. Okay, it's like a big apple. And a 320 newtons per meter spring. I don't have a good sense of that. It means to push it in a meter, you need 320 newtons, 32 kilograms. Okay. So we're going, and then it goes boing, and it goes up a meter, 1.6 meters. And again, this is measured from where it was squished to, not from the neutral point of the spring. Huh. Okay, yeah, I guess, this seems reasonable. Okay, very cool. And notice, of course, that he plugged it into his calculator. If you're a student who's like, wait a minute, how did you get that? If you're a student who canceled this 2, you'd be like, what? And you'd realize you're off by a factor of 0.2 and say, oh. So, right, there's ways to sort of catch that eventually.
That doesn't matter. All right, so the next step is, it says, how fast was the block moving when it was at half its max height? And so what we can do now is we can say, okay, well, it made it 1.6, but I want to know how fast it was moving, so we're looking for the velocity when it was 0.8 meters high. Okay, half the max height. So I'm going to turn my LOL diagram into an LOLL diagram. Oh. The system hasn't changed, so I don't need to do an LOL diagram, so I'm just going to draw this new one here. And we have our KE, cool. GPE, EPE, and EDIS. So we're going to look at our energy types. I'm going to say there was no energy dissipated. The spring is still already sprung. Mm-hmm. But GPE now, because it's halfway up.
See? This is why he wanted to do 4 blocks. This is why he wanted to do 4 blocks. Because you just heard him say it, because it was halfway up. I think he wants to put 2 blocks in 2 blocks. He can't. He's got to do a little half block. Now, of course, that's kind of jumping ahead a little bit. So I don't know if he's actually going to do 2.5 and 2.5. Maybe he'll do some here and some there. But you have these moments, right, when you plan things and you're like, oh, I'll stick with 5. And then you're like, oh, man, I wish I had done 4. So I'm really curious to see how that goes. It's graph paper, so you can do a decent half. The other thing I want to say is, what are some things that aren't going to work here? Like, oh, it's going to be the average, for the average of the beginning velocity and the ending velocity. But both of those are 0, right? The average is 2 zeros is zero. So you're not going to be able to get the speed by doing an averaging. That's really, really interesting, right? Because there are some things you can do with averages. You can say, oh, for like a cannonball shot, right? How fast is it going at the beginning versus the top? At the top, it's at zero. Halfway, well, I don't know if you can say halfway up, it's halfway there. Yeah, you can actually. So there's lots of times when we can do averages, but here's a great example where you just can't. It's zero, zero, what are you going to do? But this energy approach, I think, is going to be pretty straightforward. Let's see what he does with the 5.
Is going to be less, and KE is going to be some because it's going to be moving. So because it's exactly halfway up, and looking at my equation for energy gravitational potential, these are all direct relationships. So if I'm half as high, then the energy is going to be half as much. So I'm going to use 2 blocks and 2 blocks. And so now...
So there it is. There it is. Now look at this post-production stuff, right? He's like, oh man, I'm cruising. I'll just do 2 blocks and 2 blocks. I've done this really, really awesome description of how to rationalize the notion that it's just this half here is literally going to cut the energy in half because there's nobody in here being squared or square rooted or cubed or anything or taking a sine of it or something, right? It's a very linear relationship. So and so you can just imagine, right? So he finished this. When do we think he remembered to put this note in? That's a really interesting question. Was it right now? Was it like, after this video's over, I'm going to have to go back and fix that? Did he watch it afterwards, right? And say, oh, did a student maybe see an early version of this? This is so fascinating. I'll say it again and again and again. These critical thinking moments that teachers do all the time. I love learning how they do it because we can't expect perfection. That's stupid. What we can expect is nimble, creative, critical thinking teachers, and that's what's happening here. He's like, oh, I know what I'll do. I'll just go in there and put in a note after the fact. It's so cool. The other thing I wanted to say really quickly, and I don't think he's going to do it, but what if the spring wasn't fully released at the halfway point, right? What if there actually was some elastic potential energy? We know that it's not because it goes after 0.2 meters, the spring is unsprung, and half of 1.6 is 0.8. So it's definitely a 0 here. But I think that it's subtle, right? I think that it's important to really think about that. And so if the students are ever worried about, well, really, is this truly there? It's pretty easy. Like, look, you guys, it's going up to 0.8. I've drawn this to scale. It's clearly not touching the spring. So I think that the way he did it was really cool. And again, I just love this notes here. I'm going to go back and see how he announces that. Or I guess he doesn't announce it. He adds it later. But let's just watch it one more time. We'll go to here. There we go.
Half as high, then the energy is going to be half as much. So I'm going to use 2 blocks and 2 blocks. And so now I'm going to make a new energy expression, okay, for my part 2 here, and that shows that the EPE is equal to the KE plus the GPE when it's halfway up. And so now I need to write a new expression. Now you may, depending on how you solve this problem, you may have already solved for the EPE earlier. Cool. I'm just going to go ahead and plug in my whole expression here. 1/2 K delta X squared is equal to, my kinetic energy is 1/2 mv squared, and then that's plus mg delta h. Now I could rearrange and solve for my velocity here, or I can plug in numbers and then rearrange. I'm going to do the second method now. I'm going to plug in numbers and then rearrange.
That's cool.
And so I'm just going to go through and start plugging in numbers.
Doing it one way earlier, a different way later.
Was
That's
320 newtons per meter times delta x squared, 0.20 meters. That's squared. And that's all equal to 1/2. My mass was 0.4 kilograms times v squared. And that's plus mg delta h. My mass is 0.4 kilograms times my 10 newtons per kilogram. That's all times my delta H,
We'll just use
which
10.
for this case we went half as high. Don't forget that. Now we're at 0.8 meters. We went half the height. So this is a big expression. I'm going to simplify my life and reduce some of these things down. This first term is going to reduce down to 6.4 newtons times meters. Okay, so 6.4 joules. The last term is going to simplify down to 3.2 newtons times meters or joules. And then this other term is going to be equal to 0.2, and then we'll still have that kilogram hanging out times v squared. So I rearrange this, I subtract, this is plus, subtract 3.2 from both sides.
I mean, there's some really great points where the students can check some stuff here, right? Like this needs to be less than that, right? Because this is a positive definite quantity. So if you plug it in your calculator, right, and when you subtract this 3.2 from both sides, you better get a positive number or your calculator is going to barf on you, right? So just some really subtle things that you can check. I really, really like this idea of let's do it algebraically over here and let's do it numerically over here. Because, I mean, I'll just put my cards on the table. I'm this. This is how I always, always, always do it. And I put a lot of pressure on my students to always do it this way. But I think that he's saying, look, there's some students who can handle this and there's students who really can't. Gosh, they want to plug stuff in. So I'm going to show them how to do it, and we'll get the same answer either way. I think that's very cool.
I'm going to get 3.2 joules is equal to 0.2 kg v squared. When I divide both sides by kg, we're going to get our v squared is equal to 16. And there's going to be a bunch of units on there, and I could break down joule, and all the units would work out. But basically, when you get to the very end of this thing, our final velocity is going to be equal to 4 meters per second.
Wow, this was great. I really, really loved it. Right at the end, he was a little bit running out of space and just saying, oh, trust me, it works, which is great, right? I mean, trust those units are going to work out. And 4 meters per second, 4 meters per second is like 10 miles an hour. Okay. Interesting. Wow, really, really cool. I think my favorite part was that 5 blocks to 4 blocks. But I just love the LOL diagrams. I loved the algebraic and numeric way of doing it. Very cool stuff. All right, thanks everybody. Have a great day. And remember, physics teachers are awesome.